So, this evening we will present our 38th Distinguished Heyser Memorial Lecture. So if you would like to learn more about our past lecturers and the presentations, please visit the AS website where you can find images, names and presentation details for our previous 37 Heyser lecturers. Well, Richard Heyser died over 31 years ago in 1987, shortly after he became president-elect of the AS. So after Richard's death, his wife Amy and a group of engineers, Dave Andrews, Don Eager and John Prose, would be close to Richard, formed the Richard Heyser Scholarship Fund. It's for a generous donation of this fund that the AS is able to present this series of lectures. We'd like to express our ongoing thanks for this financial support. Now, one of the goals of the Heyser Memorial Scholarship Fund is that of creating an ongoing awareness of the work of Dick Heyser. Along with this lecture series, this effort has been greatly helped by an AS publication of an anthology of his work called Time Delay Spectrometry. So it's my pleasure at this point to announce that this anthology is now available as free PDF download to all AS members. So to obtain your own copy, just go to the special publications portion of the AS website. At this time, it's my pleasure to introduce Francis Rumsey, the chair of the AS Technical Council, to introduce this evening's distinguished Heyser lecturer. Thank you, Francis.
Great pleasure to welcome Malcolm here this evening. Malcolm Hawksford is somebody that I've known off and on for quite a number of years in the UK. He's one of the few professors that specialises in audio, and his personal career has been dedicated to the pursuit of high quality sound reproduction in a number of different forms. Malcolm is a well-recognised expert in the field, and he started out the AS High Resolution Audio Committee. He was a founder member of what was called the Acoustic Renaissance for Audio a number of years back, which was particularly interested in trying to preserve the highest audio quality reproduction. And he's also a highly decorated specialist in audio engineering, having received a number of awards, not least from us over the years. He received the AS Publications Award, and he's also received the AS Silver Medal in 2006. And then last year, we awarded him the AS Gold Medal. That is the Society's highest recognition. And so it gives me very great pleasure to welcome Malcolm to the stage tonight to talk about his personal journey in, in understanding high quality audio.
Hello, good evening, ladies and gentlemen. Thank you, Francis, for that very kind introduction. It's an absolute pleasure to be here this evening and to have the honour of being invited to present one of the Heyser lectures. I did actually know Richard Heyser briefly in the mid-80s, and I can honestly say that he was one of the great influences on my life. I started off probably around about 1976 in terms of setting up an audio research group at Essex University. And at that time, I think the general consensus was that audio was very much a hobby, and really I was just making an excuse to enjoy myself and listen to music all day. The reality was I had been influenced by Richard's work, and I could actually see from the extreme detail he put into his analyses of things and the technical quality of his papers that there was a lot of opportunity to apply rigorous academic principles to audio engineering. So I really see that as a turning stone in my personal career. So as I say, this is a great honour to be here this evening and to have that link with what I think is a very great man indeed. This is obvious, this is the content which I'm going to go through point by point, so I won't dwell on the individual points. This is going to be very much a personal reflection of my journey in academia and particular bias to high-quality audio. So maybe I'll be a little controversial at times. I've been known to do that. If the mood takes me, I might say a few things which hopefully will upset a few people. Let's see what happens. This is probably the only opportunity I will have in my life. I would also like to offer a personal thanks to the AES. They have been so influential in my career over the years, supported me through publications, I've attended many conventions over the years, and I've met so many talented people, and I consider that to be a huge honour and privilege to have been influenced and have opportunity to talk and mix with so many people. And I'm pleased to see when I look around, there's people here who I've known for years, and I've high respect for, and thank you for being here tonight as well. I would also, to conclude this part, like to pay a particular tribute to the late Patricia MacDonald. She was editor of the AES for many years, and she was an extraordinarily great help to me in preparing manuscripts, being helpful and supportive. Now, I did mention that I've been known to be, maybe touch on some slightly controversial subjects, and one of my early papers, I know, caused the AES a little bit of grief through the particular angle I told. I was young, I'd like to say it as I felt that it was. And so there was a convention at Anaheim in the early 1980s, and I thought it was slightly strange, but Pat MacDonald invited me to have dinner in the evening on one of the days of the convention. And what I realised was that I was actually being slightly investigated as to whether I was legitimate or not. Fortunately, I managed to bluff my way through the evening, and I'm still here. So I got on very, very well with Pat, and I have a deep affection for her, and I really did appreciate all the effort she put in to help me. Sensitive fingers, I'm nervous. I'll be okay in a few minutes. This is just to calm my adrenaline levels. Now, I've just thought you'd like to see some of my favourite equations. Highly influential. I mean, all the things we do, the fact that much of it can actually be focused on a set of simple, not so simple, but simple equations which explain basically how electricity works. I find that fascinating. Now, as you probably know, there's going to be a test after the lecture, so I'd like to emphasise that these equations will be part of that test. However, I'm a generous person, so I will be awarding 10% if you spell your name right and put the correct date on the Having said that, that is no guarantee for success. I talk from experience. Some students don't really calm down. Okay, let's move on. Look at this frivolity. One of the pleasures of being an academic, and probably the greatest pleasure and the greatest satisfaction you can have, is the students, and particularly the research students who you get to work with over the years. And I've been privileged to know some truly excellent students. And I think there is something about audio, particularly its relationship to music, that actually produces some of the best students that you can have to supervise. And there's maybe, if you look down this list, there's one or two names, or a few names who you probably recognise. There's Mark Sandler, for example, very well known for his work on PWM and related topics in audio signal processing. Richard Hughes, possibly not so well known, but he runs a company, LFD Audio, and makes some absolutely superb amplifiers. And when he was my research student, we worked on digital crossover networks. And back in the mid-1980s, we had a grant from Canon, and that work actually led to one of the first digital and active loudspeaker systems, eventually taken to Japan. Usually things go the other direction. But on this occasion, it was taken to Japan and demonstrated at their research centre. Other names who you may know, Mike Collier. He's now with Dolby Laboratories. He used to be with BT Telecoms. We did a lot of interesting research there. Another name which grabs me is Graham Bank, who's technical director of Celestine International. He did work on ribbon loudspeakers and applying FEA modeling to those devices. And last, but by no means least, sorry Adam, you're at the bottom of the list. And then that's life, it's tough sometimes. The reason being, he was actually my very last research student. I'm absolutely delighted that he's been present for this evening. He worked on what he called Schmidian loudspeaker systems. If you want to know what a Schmidian loudspeaker system is, please have a word with Adam after you go. It's a way of producing a very even distribution of low frequency sound in a given environment. I'm sure there'll be a lot of you who have a strong interest in that subject. It's also been widely published in the AES, so you're probably already familiar with this. Now I'm going to get through this part quickly, because I know what Francis told me. He said, don't spend too long on the introduction, because you won't have time for the bits at the end. But I have to mention, I like to think of myself as the third generation of audiophile. My grandfather was the one on the left, collected 78 records. He actually made his own electric gramophone. He had a separate loudspeaker with it in the times when this was relatively rare. And I'm told, and I don't know if this is true, but in the 1920s he would put his gramophone in the bedroom window, and people in the street used to gather around and listen to a record player. If you did that today, a little man from the council would come around with a microphone and you'd probably end up in the magistrate's court. Times have changed. My dad was also very much into music and hi-fi. He introduced me to analog reel-to-reel tape recorders, which was one of my great loves when I was a teenager. He bought a Grundy TK-820, I think it was 1959. It was absolutely fascinating, so I owe him a huge debt of gratitude. And then there's me on the right-hand side. What you can see from these slides is just how clothes and dress have evolved from the early 1920s through to the 1940s to the modern era of 1960. I'm not sure it actually is progress. This was the time of psychedelia, of course, and I had an ultraviolet light in the bedroom and a few posters on the wall which used to light up. I remember starting now on the journey in audio, I remember as a boy in 1950 asking this question: how can a loudspeaker cone made of paper sound like a brass band or a violin or even Elvis Presley? If anyone knows the answer to this, come and see me afterwards, please, because I find it totally fascinating. Something as unmusical as a piece of paper can sound so wonderful. Even that little electrical drive unit had its day. Well, I mentioned tape recorders. One of my misspent youth was designing and building analog tape recorders. This was my first incarnation, a mono machine, which actually featured in Hi-Fi News and Hi-Fi News and Record Review. I think it was 1965. So that I cite as my first publication. I used the Brunel Series 3 Mark V deck. It was a nice piece of work. Now, I know also some of you are interested in radio masks. I know people collect huge amounts of data on this. They can tell you the number of guide ropes. They can tell you the number of steps from the bottom of the mast to the top. But this particular mast holds a strong affection for me. It's the one at Sutton Coldfield, just outside Birmingham. And in the 1960s, it's where the first stereo FM transmission was made into the Midlands and the area I used to live, Shropshire, in the UK. And this is where, for me, stereo started, with that transmitter. At the other end was my own second generation tape recorder, and I was the proud owner of an FMT Radford tuner, which had a stereo decoder, ready for this big occasion. Very exciting times. We didn't have iPads and stuff, but we did have stereo transmissions on. And I remember, the British are very conservative, and the BBC is even more conservative. It certainly was in the 1960s. And the first stereo broadcast was on a Sunday evening, I think it was, at 10 a.m. And it was a jazz program, and Humphrey Lyttelton was comparing the show. Now, you really won't believe this. Just before 10 o'clock, the little green light came on the stereo decoder, We knew the stereo transmission was there. The noise level went up. We didn't have MPEG artifacts in those days, so it was just pure noise. A little bit, a few dB of extra noise due to the multiplex control. And then the announcement was made, this broadcast is going to be in stereo. And Humphrey Lyttelton said, and the first record we're going to play tonight is a mono recording. Now really, take the occasion, you know. We move on. I was educated. I went to Aston University. This is me as a research student. I'm the one on the right-hand side, by the way. Cheeky. And this lab, what I like about this particular lab, fond memories, is the lab where I made my very first sigma delta modulator. And I remember playing music through it, and I was going to turn it into a guitar effects device. It actually could produce lots of distortion in the right parameters. I think I've missed my opportunity now. So my interest in sigma delta started in 1968, and I actually built my first coder at that time in that very lab. If anyone wants to repeat these experiments, the equipment which you see, most of it can be bought very cheaply on eBay now. We also had computers. This was a portable computer, at least it had wheels on. We've moved on a little bit. Great fun. And finally, before I start my real talk on audio, my PhD was about the application of delta modulation to colour television. Yes, I know it should have been audio, but it was colour television. And I came up with a technique for encoding the luminance information, and I made a first-order sigma delta coder running at 100 megabits per second. I had to use MECL logic and transmission line layout on the board and all that thing. I thought 100 megabits was pretty good from around about 1969. And it also used a lower bit coding for the chrominance information, and it time compressed the chrominance information and slotted it into the line blanking period. This is before the sort of satellite broadcasting that used time compression. So this idea appeared from here. So I had quite an exposure to delta modulation and sigma delta modulation. And there's one concluding paragraph in my PhD thesis, and I put this up because actually it's one of the few times I felt I predicted the future a little bit. It said, it is now possible to design a system that uses only a digital filter and a single analog filter. Basically, a digital filter reconstructs the delta modulation pulse waveform from a knowledge of the PCM samples. The delta modulated pulse sequence is now applied to an analog filter where decoding is completed. Lo and behold, we now have a world full of sigma delta modulators, upsampling conversion and simple analog filters. So, yeah, little vision mistake. Right, high quality audio. What's my philosophy? Well, probably I put at the top of the list, keep it simple. I know this is bad news for the recording industry, but the big enemy of sound quality is complexity and over-processing. Don't use any more signal processing that is absolutely essential. I'm talking about here high-quality recordings which you want to be as realistic as possible. Personally, and this is a personal preference, I prefer to use a true R2R ladder D2A converter. Even though I work on sigma delta, my preference is for a non-processed R2R ladder network. It's direct, it's immediate, there's no loss of information in signal processing. And I like to run them in without upsampling conversion. So it's what's called an NOS, no oversample in filters in the system. I've also learned, much from hard experience, that the digital interfaces require extremely careful attention, particularly things like USB connections between a PC and a DAC. In fact, getting the interface right seems to have a bigger impact on sound quality than changing the sampling rate. You've got to get everything right, but then having a clean USB supply with a clean DC supply and regeneration can make quite a difference, even, believe it or not, with DACs that claim to be immune to the interface. So there's something going on. It's basically to do with interference and jitter. Oh, and avoid amplitude compression. Whoever invented the amplitude compressor needs shooting quite well. Just lock them up or throw away the names plug. It's killing modern music. It is horrible. You can tell just by looking at the waveform on the oscilloscope. It truly is destroying sound quality. It's on the radio, it's on CDs, it seems to pervade everywhere. So I make a plea. There was a wonderful workshop in New York in, I think it's 2014, highlighting this problem and saying what a massive crisis it is. And something has happened. Maybe one should be familiar with it. Young people now listen to audio. They listen to highly compressed audio, and their neural nets are wiring up to believe that that is correct, that is normal. And when the compressor's turned off, they think something is wrong with it. Now, okay, there may be a case for re-education, but I find that very, very sad. So, please turn off the compressors. And obviously things like keep the power supplies clean. And here's a controversial point, don't put too much silver in the wires in audio systems. I think it gives it an unnaturally bright edge to the sound. Okay, more controversy. Here is the Oxford conjecture. My claim to change the world. Surprise, surprise, we only hear signals within the audio band. Let's be generous and say, I'll say up to 25 kilohertz. There are a few people who have hearing into the lower 20s. Majority of us don't. Sounds obvious, doesn't it? You hear what is in the audio spectrum. And I also propose that any changes in sound quality are entirely because changes that occur due to audible band signal components being altered in some way. Nevertheless, although ultrasonic information is not directly audible, this is the crux of the matter. The process and consequence of its removal can become audible. The very signal processing we use, the filtering, the techniques, are what I believe are at the heart of the change in sound quality. It isn't the presence of ultrasonic stuff, it is the presence of signal processing, particularly things like sample rate converters. When you think what happens, the studio downsample converts, maybe once or twice, maybe more times. Then there's oversampling filter in the CD player and the D to A converter. Each one introduces a loss of information, introduces errors. One of the beauties of high-resolution audio at a reasonably high sampling rate is that it really bypasses the need for sample rate conversion. You've got this advantage which comes by having a higher sampling rate, but you don't need the sampling rate converters. And all things being equal, with high quality recording, you potentially have the opportunity to produce high quality recordings. So there can be advantages in higher sampling rates, but I maintain that the audibility of ultrasonic information isn't the key feature. It's the removal of the ultrasonic information which can have the biggest detriment. We're going to come back and visit that, so I won't spend too much time on that. Right, I'm now going to reflect. We're going to do some stuff on digital and some stuff on analog. Analog is part of my passion. So let's reflect on some digital stuff. So I'm going to, something we all know, but I just want to put a slightly different gloss on it. So fundamentals of digital audio, as we know, there's time sampling, there's amplitude quantization, and I include dither in the fundamental. Because with LPCM, the correct application of dither, as Stanley Lipschitz has so ably instructed us, converts the PCM channel into a linear, noiseless, noisy system. There's a little bit of noise, but it solves the linearity problem. All things being equal. Because that's what the theory says. What the practical instrumentation does may well be different. There is, of course, jitter. It's not exactly fundamental, but it's pervasive. And it's an unavoidable and unwelcome intruder. Very hard to avoid, often bigger than you think it is. So, when I was a student, I asked the question, I think it was in 1968, how did the fundamentals of analog to digital converter relate to our understanding of analog processing? The reason I asked this question was I was trying to show off in front of my supervisor. When you're supervising a PhD student, it's this battleground. The master is trying to show the student how clever he is, whereas the student is trying to do just the opposite, to show that the master is making mistakes and he doesn't know everything he claims to. So this is my claim. So let's look at this. I think it's interesting because in this few slides, it encapsulates a huge area of audio engineering. First of all, time sampling. This is what we're obviously all familiar with. We start off with a regular sequence of impulses. We then take our analog signal, and effectively just multiply the two together and get a sampled signal. This isn't a digital signal, this is a sampled signal. You apply a sample and hold, and you end up with the waveform at the bottom. The sampling signal can be represented by a Fourier series, and if we multiply that by the input signal, we get the equation at the bottom. The phi term is the desired information. The sub under the sigma sign is all the distortion which occurs due to sampling. But if you look carefully at that expansion, it is just the product of a cosine carrier wave and the input signal. It is simply double sideband amplitude modulation, albeit the spectra, as we know, is repeated many times. So, time sampling is amplitude modulation. There's a wonderful relationship between classical analog techniques and sampling. Maybe one you haven't thought about quite so much is amplitude quantization. And I put to you that amplitude quantization is actually a form of phase modulation. Let's start again. Let's start with a regular sequence of samples, exactly as we did with time sampling. But in this case, the horizontal axis is the time function phi. It isn't time, it is the function phi. It's the instantaneous amplitude of the signal. And what happens is that signal gets sampled at uniform periods of time, possibly every 2 pi, for example. And it's called natural sampling. We sample the signal when the amplitude is in a certain state, when the amplitude has changed by, let's say, 2 pi. It doesn't have to be 2 pi, but let's say it does. So if we take that sampling signal and we apply a ramp input signal, what we would get is the middle waveform. And if we apply a sample and hold, you get the classic quantizer characteristic. Now again, we can perform a Fourier series analysis on that, and we get the expression shown in the bottom right-hand side. Again, the phi term comes out, that's the side undistorted signal, and all the stuff on the other side is quantization distortion. But if you look at it, it's an infinite sum of sine waves, where the phase of the sine wave is being modulated by the input signal, hence phase modulation. So, we can now think of quantization as phase modulation. Now, if we look at that expression, top left-hand side is taking just the first harmonic, and we're imagining a ramp signal being applied to the quantizer. And if you look, it generates a sine wave. We're just taking the first term. It is one way of producing the sine wave. If we add in 3 harmonics, we get the curve on the right-hand side top, 10 harmonics bottom left, 100 harmonics bottom right, which you increase the number of harmonics so it gets more close to the classic staircase waveform. So I like to think of amplitude quantization as a form of phase modulation. Well, if we apply a ramp signal to the input of the quantizer, and let's imagine now we sample it at the 0 crossings of the sine wave. Those are the natural sample points. If you take the positive 0 crossing, they're all 2 pi spaced along the phase axis. And so take a ramp signal, add to it our input signal, superimpose it on the ramp, and we end up with linear frequency modulation. Now for this waveform, you imagine a deep zero crossing, a little impulse is applied, and all the impulses have the same weighting, all the same shape as well. And what is wonderful about that naturally sampled signal with an FM modulator is that it is virtually linear. Look at the spectrum. There's two tone input signals applied, and what you see is that the noise at the bottom is due mainly to the lack of resolution in the computation. We're down at minus 300 dB, so it's pretty linear. And then you see the sidebands of the FM at the top. So naturally sampled signals with a carrier introduced by applying a ramp signal to the input gives us this. And this is essentially the core of pulse width modulation, naturally sampled pulse width modulation. Now there we use a triangular wave and a comparator. But that's essentially the same as having a uniform quantizer with a linear ramp. So the two are related. So we've moved on. We've now embedded pulse width modulation in our notion of a quantizer and phase modulation. Of course, jitter plays its ugly head in all these things. And on the right-hand side, I took that and I perturbed the samples each by 1 picosecond. Not very much. A little bit of random jitter was introduced. And you can see that the noise floor, it still looks pretty low, but it's actually increased by 100 dB, just with 1 picosecond of jitter. It's down at minus 200 dB, so it's still pretty small. But it's had that influence on the signal. So jitter, of course, is the enemy of pulse width modulation, as well as A to D and D to A converters. Well, what about sigma delta modulation? Can we bring that into our sort of simple understanding of phase modulation? Well, this is something I again did as a research student. So this was around about 68, 69, I think. You take a linear frequency modulation, or frequency modulator, I should say. You extract the positive zero crossing. So here you can see an FM signal in the middle. I can find the cursor, it seems to. Here it is. Here's the FM signal. Here are the positive zero crossings where these black dots exist. And what we're going to do, these are the natural sample instance, remember, which on the FM model gave us almost perfect linearity. We're now going to approximate those to certain time slots. So remember with sigma delta, it is a digital signal because it's discrete in time as well as amplitude. And so what we do, we're just going to approximate the position of those zero crossings to the nearest time slot. And when you do that, lo and behold, you produce a first-order sigma delta modulator. So essentially, the first-order sigma delta modulator is an FM oscillator, modulated FM oscillator, linear FM modulator, with some timing error. Now you can think of that timing error as a form of jitter, because we've jittered the point. So really, first order sigma delta, you can think of it as basically linear frequency modulation with the introduction of some jitter due to the time quantization of the signal. Now, of course, with higher order sigma delta modulators, what we're trying to do is to noise shape that jitter so that its spectrum is low in the regions where the audio signal exists. Well, this is just a pictorial model. At the bottom you can see a man eating his violin. This produces sound, which is well known in orchestral circles. This radiates in all directions, and of course the recording engineer comes along with 1 or 2 microphones, sometimes more. And so there is a massive loss of information. From what the microphone picks up, you can no longer work out what the vibrational patterns of energy are in the violin. So there's a great loss of information, never to be recovered again, unless you use a myriad of microphones, of course. So that, we would say, is an increase in entropy. There is information which has become hidden from us. It gets propagated through the air. Good idea. Air, of course, the velocity of propagation depends on the pressure. So when the pressure goes up and down, the velocity gets modulated. Now I know it's not very much, but there's a little bit of jitter introduced in the air. If anyone's interested, I'll be selling some audiophile air, which I bottled earlier, which will be on sale after the lecture. Only £100 a bottle, real bargain. Then we hit the recording industry with all its myriad of processes and conversions and sound effects. And of course, entropy rises even further. Come back to the point that every stage, from the microphone to the microphone preamplifier to the cables to the first A to D converter into the system, each time a little bit of information is lost and cannot be recovered. So that's my belief that you should minimize and keep the signal path as simple as possible. In the consumer domain, we see similar problems. The quality of the reproduction equipment, the processing which goes on in D-to-A converters, etc. All that conspire to increase entropy. You cannot avoid the second law of thermodynamics. It will get all of us in the end. It will all do. Right. Sorry. Okay, approximate resolution diagram. Well, I said I fundamentally really believe that all the activity occurs in the audible band. And there may be a few shades either side, and this is just diagrammatic. It shows increased bit depth and increased bandwidth. Remember that when we get into the grey areas, particularly on the right-hand side, we're essentially deaf to the sounds which are there. Now, I know there's masses of arguments. I've heard all the arguments in high resolution, or maybe not all of them. I've heard quite a few. Some of them sound almost convincing, but I still experience tends to tell me that the changes are occurring due to problems with the equipment and problems due to the processing which goes on. In terms of bit depth, what about going beyond 16 bits? Well, there's a little bit of advantage maybe going from 16 to 20, but when you go below that, it turns into noise. Now, if you've got a 16-bit system, signal, what should you do with it? Should you just play that? Or should you convert it to a 24-bit system by actually adding noise in the last 8 bits? Now actually, when you play that through things like R2R ladder D2A converters, the addition of a little bit of low-level noise tends to smooth over the cracks in the converter. It actually dithers the signal, not in the Stanley Lipschitz sense exactly, but it tends to iron out some of the imperfections which appear in the D2A converter. And in many recordings which aspire to 24 bits, actually once you get below about maybe 18 bits, it's mainly noise which you're tending to see, or at least those signals are noise-like. And I bet if you took the lower 8 bits and substituted them with random noise, you'd be hard-pressed to tell much difference per bit. You might, if you're very sensitive, hear a slight increase in noise level. But the absence, filling those bits with zeros, may well be audible. But that again is often due to the D2A converter, etc. There is some advantage. When I say adding noise, be very careful. I mean adding noise in a way that literally just exercises the lower 8 bits. If you chop those bits off, you get back to the original signal. There's no loss of information in the recorded signal. So make that distinction. We're not playing around with the low noise level of the audio. It's not actually adding noise to the original recording. It is adding it in the data set which does not contaminate those bits which sit above it. So I actually process all my CDs and convert them to 24 bits. I believe it makes a difference. Sometimes it does, sometimes it doesn't. Now I'm going to be very naughty here and upset you all. I'll try to get through this quick because I'm playing Francis card, being a little bit too slow through this stuff. So, what do high-resolution people get excited about? Well, certainly listening to ultrasonic audio must be one of them. Minimum phase SR sampling rate converter filters, clearly another. If your sampling rate converter doesn't have a minimum phase filter, there must be something wrong with it. Employing the highest possible sampling rate, yes, a lot of people do that. You can choose, you could use a 32-bit or 1-bit depth. That very much depends on your mode. I've even come across monitoring brain waves while listening to ultrasonic audio. That's a relatively rare activity, but I believe it goes on. From an academic point of view, it's a good idea to use a log plot to exaggerate the SRC filter's impulse response, because it looks bigger plotted on the log scale. And another argument, which is really quite interesting, is justifying ultrasonic audio content based on snapping a twig. You must have heard this argument at times. It's something to do with our ancestors and trying to survive in the wild. But of course, they had stereo perception, so I don't know if it's quite a true analogy. Helps if you've got an exotic name for the filter which you're using. And the marketing people tend to like to relate the cost of the sampling rate and bit depth. Okay, let's be a little more scientific. Digest at times. Let's talk about this minimum phase filter thing, which everyone gets excited about. Really thinks it's the best thing since sliced bread. Top left hand, we see a filter which is designed to have a cutoff close to 20 kilohertz. Now, in any practical filter, you have to truncate the length of the filter to make it finite. And you probably use truncated coefficients to generate it. And then there's the arithmetic which does the accumulation. That will have a finite word depth. And then you finally truncate the signal. You locally do it. So there are imperfections. So the real curve may look something more like the red curve. It may actually not have perfect suppression in the ultrasonic band, and it will have some degree of ripple, although hopefully very small, in the pass band. And of course, the phase response will be nonlinear, unlike a linear phase filter, which will have a linear phase. But let's look at the two responses. On the bottom left, we see classic linear phase IR filter, a nice sharp cutoff. And then we see the minimum phase on the right-hand side. I'm not going to explain why it's minimum phase, but it's all to do with causality. But you can see that it sort of starts and then there's a big spike and then it oscillates. So there's nothing precursive about it, which is one of its supposed attributes. But let's assume it's the ripple that does the damage. If you actually look at the ripple duration between the linear phase and the minimum phase, the time scales are not the same. But with the linear phase, it's about 100 samples, and with the minimum phase, it's about 200 samples. It persists a little longer. But look at the peak of the first pulse. It actually sits at about -0.6, whereas with the linear phase filter, it sits at -0.2. And the first positive pulse is approximately 4 times greater than that of the linear phase filter. So, we've exaggerated the ripple actually with a linear phase filter. So I'm very skeptical about this, and so I run a little experiment. And I built myself a sampling rate converter using a finite impulse response filter. So I could take either a linear phase or a minimum phase filter which had been truncated. Now if you take a minimum phase impulse response, it may have some slight irregularity in the pass band, potentially may be audible. But if you time reverse it, the amplitude response stays the same. It doesn't change in any way. But the phase response does. It goes off in the opposite direction. So, you perform this experiment with the time reversed impulse response, and you can listen to the two. They have the same amplitude response, so you can't argue that I'm hearing a difference due to a change in amplitude response or in-band ripple. And when I did the experiment, quite bluntly, I mean, I'm not the one to make the judgment, but I couldn't tell any difference between them. So if there is a difference, it's subtle. And I really come back to this crux of my argument, that any changes are due to errors which occur in the audio band itself. And I think it's false. President Trump would say it's fake, that a minimum phase filter is actually better than a linear phase filter. Of course, no filter at all, no sampling rate converter is even better still. So I leave you with that to think about. But think about the amplitude ripple which occurs with a minimum phase filter. Okay, insight into analog circuitry, moving on to my second part. So here are some analog circuit building blocks. Now after I drew this, I had wondered what would happen if the bottom right-hand brick were to slip. It makes my eyes water to think about it. Some basic circuits, I won't harp on too much. Common emitter amplifier, very common. Grounded base amplifier. But one maybe you haven't seen, or at least not so familiar with you. And we call it the common current mode asymmetric cell. Now if you look at it, it looks slightly odd, doesn't it, in that the input is applied halfway between these two resistors R1 and R2. But what happens is you apply the input to output, current flows from right to left through R1, it circulates through the transistor and it comes back into R2. So the current actually forms a closed path in that circuit. Doesn't flow through the ground rail at all, so we've got to worry about grounding problems. And it's closed, so the input impedance of this, well, the input current is actually, in this case, equal to the base current of the transistor, because that's the only current that flows away from the circuit. And what's also interesting is that part of the signal is actually fed forward directly through R2. The unity gain part goes directly through R2 to the output. And then what goes through R1 is like a grounded base stage, but that current comes back, flows through R2, and you get a gain which is 1 plus R2 over R1. On the top right-hand side, there's an enhanced circuit which uses a current mirror and an emitter follow at the input. And if you were to look through and analyse that, you'd find it actually helps lower the output impedance of the circuit, so it helps with loading and improves the linearity a little bit. So there's an alternative. And I actually built a preamp years ago based on this technique, and it did sort of work quite well. It had a very good bandwidth, and I like the idea that there was this almost direct coupling between the input and the output of the basic cell. Well, circuit stages we're all used to. Common emitter stage has certain nonlinearity. Use the metric of incremental distortion factor, which was something I introduced in the early 80s. X is the loading factor of the circuit. It represents the ratio of signal current to bias current. So it has a range approximately plus or minus 1. And you can see that for the common emitter amplifier, it's equal to minus X over 1 plus X. So it's asymmetric, which of course is what you expect. The incremental distortion factor is simply the slope of the transfer characteristic compared with the slope when the signal tends to 0. So it gives a measure of nonlinearity. The long-tail pair does a lot better, fares a lot better. It's proportional to X squared. And on the right-hand side, if you combine the two together, you can sum the two incremental distortion factor, and that circuit is almost completely linear. Now, I believe when you're designing high-quality circuits, it's the detail, and you need to keep it as simple as possible, but try to get the best possible performance from that elementary circuit. And that led on to looking at cascode circuits, and I came up with this circuit, which is illustrated in the middle. Most amplifiers will have a cascode as their second stage. And this uses what I call the enhanced cascode, and it's almost virtually independent of the slope resistances of the output transistor. So if it's used in a power amplifier, for example, where the voltage swings by quite a lot, even if RCE and RCB are non-linear, because the currents flow through closed paths, it has very little effect on the output. So two things happen. The output impedance increases significantly, which gives the circuit more gain overall when you look at a complete circuit, and it becomes more linear. And yet all we've done is move the connection to the biasing supply, it's this one, from there to there. So the currents now can only ever flow through distinct closed paths. That is published if you want to get more information. Preamp design, well, again, something I've always been interested in. Had a crave a few years ago for building low feedback designs. So the basic of a low feedback design is to have a transconductance input stage which pumps current into the RIAA network. So the gain of the circuit is simply GM times the impedance of the RIAA network, and you have a buffer amplifier. Conceptually very simple, no overall feedback. This led to a prototype which combined the complementary topology we just talked about and literally produces a high impedance output, drives current in the RIAA stage and the buffer. But what was original, but it was almost unique, nearly the same thing, is that the circuit used completely floating power supplies. Now the consequence of this is, even if these power supplies are imperfect, and they have a little noise waveform, the currents which they introduce into the circuit can never find their way through the RIAA impedance. And so the circuit is almost completely insensitive to the power supplies. But of course, the power supplies are going to be good in this case. They were lead-acid batteries. They're pretty ideal. But even so, the circuit is very insensitive to power supply. And particularly when you're dealing with microvolts of signal in a, say, moving coil disk stage, that's extremely important. This led to Richard Heyser, who I mentioned earlier. One of the first products he was produced took this basic topology and converted it into a product. He no longer makes it, but this was the prototype. And you can see all the lead-acid batteries, all floating, and it worked extremely well. The RIAA network was plotted using good quality parts, which Richard is expert on choosing, and precision switched attenuators, etc. This still works brilliantly to this day. Good circuit. And at that time, I was friends with Alistair Robertson-Aikman, famous for SMEs, Return Table Company. And this is his, or was, unfortunately, he's died and he's dead now. But this was his listening room, one of the best listening rooms I've ever encountered. And we used to be able to evaluate equipment and stuff there. And he got some modified quad electrostatics, and those speakers sounded absolutely superb. He was a fantastic guy who made some superb products, and of course the legacy of that company is still available today through their turntable production. Also, the use of feedback is clearly important, and I was involved with a design recently with Armour Home, and we wanted to design a low-level preamplifier. This one uses negative feedback. And it uses a combination of a transconductance input stage and a transimpedance output stage. But the novelty in this circuit is that the transimpedance output stage is actually configured to be second order. So it's a little bit like having two cascaded integrators. It gives you more loop gain, because you can have a region where the gain is flat, it then rolls off at 12 dB per octave and then levels out at 6 dB per octave. There's the actual topology with the capacitors in place. And I'm hoping this will get released under the Goldring name later this year. It's looking good at the moment. And there's some simulation. If you look at the open loop gain, which is the red curve, you can see the region where the gain rolls off at 12 dB per octave and then bottoms out to 6 dB per octave, and the phase response comes round. So it gives you very good stability. And it deals with the fact that you've got the RIAA network in the feedback path, which of course gives you phase advance. The gain is increasing in the feedback path. So you can take advantage of that by having this second order transfer function in the forward path. And you do it without cascading two stages. The idea of putting two cascading amplifiers is not a very good idea. I wanted to keep it simple, high quality front end, unity gain buffer, but a bootstrap unity gain buffer to give it a second order transimpedance characteristic. So again, little details can help you in designing high quality circuits. I want you to note the time. We used to work late at Essex, 5:10 in the afternoon. Error correction, one of my pet subjects. I got inspired by the work of Peter Walker back in the 1970s with his current dumping amplifier, and that got me thinking. And when I moved into Wivenhoe, where I live in just outside Colchester, I moved into this house which had just been finished, and it wasn't properly dried out, and it was winter time. It was down. And I got terrible flu, one of the occasions in my life when my temperature rocketed up to something rather high. And I hallucinated. I remember having this dream, I had a vision. And basically it was the concept for error correction. So I wrote it quickly down on a piece of paper and then worked on it later. But there is something very profound in the idea of using a combination of feedback and feed-forward. Now, in a feedback amplifier, for it to be ideal, you theoretically need the loop gain to be infinite. Now, clearly it can't be. We know it has to fall with gain high frequency for stability, which means that the distortion, performance, and all the things that go wrong with amplifiers tends to increase with frequency. So, if we're going to have an amplifier which is totally, pretty ideal, we need to do something more radical. And this is, as I say, grew out of the work of current damping, but it's sort of reverse engineered. Here we see a topology where n is a nonlinear amplifier. Think of it as a unity gain stage, where n is close to 1, but it varies due to distortion. We can measure the instantaneous error voltage by having a difference amplifier. Now, of course, if n is very close to 1, but that error voltage is very small. So one of the significant features of error feedback is that the error amplifier does not get exercised very much, because we can keep, hopefully by good design, the error small in the first place. And with this structure, you feed back a fraction A to the input, and you feed forward a fraction B to the output. Now, without going through the analysis, it turns out that if you make A plus B equal 1, then that circuit is completely independent of n. We've completely corrected for the nonlinearity. So this means that in the feedback path, we could make A a first order filter, maybe place a pole at something like 500 kilohertz or so. So as we approach the point where A starts to diminish in gain, it starts at 1 and it starts to fall. What we actually do is to allow B to increase. And we do it in a way such that A plus B is equal to 1. So if A was 1 over 1 plus ST, then B would be ST over 1 plus ST. A would be a first order low pass filter, B would be a first order high pass filter. It's actually the same problem as a constant voltage first order crossover network. So that structure overcomes the limitation of pure negative feedback. The combination of the two actually can linearize the stage n. So how do you apply this to an amplifier, for example? Well, if you take the special case of B equals 0 and A equals close to 1, then we have what is called pure error feedback. There's no feed forward. To turn it into an amplifier, here you see the difference amplifier measuring the error voltage V epsilon. There's then a transconductance stage which converts that current voltage into a current such that it flows through resistor R1. And if you make GM R1 equal to 1, you can see that the voltage drop across R1 is equal and opposite to the voltage drop across N. They sum to 0. That's the ideal case. Of course, A can't be quite equal to 1. You've got to roll it off a little bit for stability reasons. But that's how error feedback works. It is strictly just negative feedback. But it's error feedback because you're only feeding the error. You're not feeding the output. That's the distinction. You're taking the bit, like the output stage of a power amplifier, which is non-linear, and you're feeding that back. And if you make that error small, then the error amplifier is only exercised a small amount. And there's a practical incarnation of the circuit using that principle. T5 and T6 are Darlington output transistors. T7 and T8 are the error sensing amplifier, which is then fed back through T1 and T4 to the input, and T2 and T3 are classic amplified diode biasing circuits for that. So you have to adjust the value of R1. If you can't afford a distortion test, it actually turns out that when the circuit is correctly balanced, that the output impedance goes to 0. So if you switch a load on and off, and you adjust R1 to the point where the voltage doesn't change, you're pretty close to the optimum balance condition. If you over-adjust it one way, the output impedance rises. If you go too far the other way, the output impedance goes negative. So when you connect the load, the voltage goes up. There's one problem. The ideal situation is when it doesn't change at all. When I looked at this circuit, however, I thought, well, there's 1, 2 extra transistors. Can we actually make the amplified diode part of the circuit, that's T2 and T3, which are there to bias the output stage, can we actually make that part of the error amplifier? And this is the circuit which I came up with. So TB1 and TB2 are the bias transistors, T3 and T5 are dominant and output transistors, and you'll see that the potential divider to set up the amplified diode. But there's an additional 2 resistors R2, and if you choose all the parameters correctly, those are the equations telling you how to do it. Lo and behold, the bias circuit actually acts as a local error feedback. Note, the circuit is very simple, fast-acting, simple, dealing with the output distortion of the output transistors. It doesn't have lots of op-amps and complication, that kills error feedback. The idea is to make it local, fast, simple, and accurate. This circuit gets pretty close to that. So what you do in practice is to have top is a conventional feedback amplifier. Of course, what happens there is all the error of the output stage gets fed back through the feedback network to the input. So the input amplifier has to process all the crossover distortion. If you apply local error correction to the output, you remove that distortion signal in the feedback path. So you get the enhancement of feedback and the advantage of error feedback. So with error feedback, you can probably get a 15 to 20 dB reduction in distortion and a lowering of output impedance, and then the advantage of overall feedback. So it's not necessarily a substitution for overall feedback, it just fine-tunes the circuit, and in particular, it takes out a significant distortion which would normally flow around the circuit, potentially causing intermodulation in the input stage. Because a lot of the crossover distortion can be at high frequency. Finally, if I look at the feedback feed-forward topology again, and I split it down, so the top right hand, if you look carefully at it, you have to blink because it'll be gone soon, is actually the same circuit. I've just replicated the error amplifier for the feedback and feedback, rearrange the input circuit to what the circuit in the middle, a little bit of fine-tuning, introduce the feedback amplifier, and lo and behold, what you have is the classic current dumping feedback amplifier, which Peter Walker introduced in the 1970s. Lots of discussions of how it worked at the time, but I think its linkage to error feedback feed forward is the fundamental point. And there's 2 possible incarnations of current dumping amplifier. You can either have an output inductor, L2, and resistor R1, or you can make the output R2 with the feed-forward bit being capacitive. Both those can meet the balance condition. We haven't got time to go into that now, but I just wanted to tell you the linkage between error feed-forward, error feedback, and how in many ways the current dumping amplifier conceptually embeds those important features. One final little wrinkle on this theme. You can see the top left-hand picture, there's a donut with a wire running through the middle and a coil of wire on it. Well, if you make it to the magnet rather than dome, it becomes a current transformer. So what it tells us is, and if you remember the electromagnetics, you take the line integral of H dot dl around the center of the toroid. By Ampere's circuited law, it will tell you the total current which flows through the surface created by the contour. It doesn't matter where the wire goes, it just has to circle around it. So there's a little model I made, an actual current transformer I made with a little ferrite ring, and there's some waveforms. Triangular wave at the input. Remember, it differentiates the signal. So if you put a triangular wave in, you get a square wave out. Actually, that little transformer has a very good bandwidth. Why am I interested in this, you ask? Well, once you have your current transformer, you can start sticking it in various parts of your amplifier topology. So if you look at the top left-hand picture, where you've got current I1 and feed-forward resistor R1 and I2, you can put a little current transformer there and then apply the signal in the feedback loop. Now you have to get all the parameters balanced and things, but there's the opportunity of making it like a current dumping amplifier, but without the impedances of the output. It gives you a little extra flexibility you may not have thought about. So I just plug that idea in as something, if you want to work on an original circuit, there is potentially a good application for using little current transformers to sense certain currents and apply clever feedback. Right, final subject, spectral domain approach to downsampling rate conversion. Well, you probably gathered I'm not the world's biggest fan of sampling rate converters. That's why I spent the last 2 years trying to design one. One of the big bugbears of the sampling rate conversion is the use of a low-pass filter, digital low-pass filter. Wouldn't it be interesting if we could build a sampling rate converter that didn't need one? And you wouldn't have to choose whether it's linear phase, minimum phase, whatever. So let's look at the problem. I'm going to show you two designs of low-pass filter. One is going to have a total FIR length of 101 samples, and another of 401. One will have a transition band of 1 kilohertz, close to 20 kilohertz. The other will have a much narrower band of 100 hertz. So let's start off with the example 1, which is the lower specified one. Now, once you start truncating filters and putting in truncated coefficients and truncating the impulse length, you degrade its performance. And what happens is you get ripples appearing in the passband, and you get imperfections in the attenuation band above the cutoff frequency. So, on the left-hand side, in the middle, there is a low-pass filter, which is shown by the black curve, and you can see all the ripples which are occurring in the stop band. But in the red curve on the left-hand side is actually the error between the target response of being flat and what the actual low-pass filter does. So you can see there's almost a mirror symmetry between the ripples in the two for this particular example. Okay, so the red curve is what's appearing in the audio band, and that produces errors. Now, let's test it in a slightly unusual way. Rather than just looking at that frequency response, let's imagine we had a signal at 176 kilohertz that consists of 8 samples, which I'm going to choose at random. And I'm then going to pass that 8 samples through the low-pass filter and then compute the error which occurs due to sampling rate conversion. So if you look at the top of the curve, let's here, this bit. This happens to be the particular spectrum of the 8 samples I've chosen. The blue curve on the right-hand graph is the error due to the frequency response ripple within the audio band. Okay? The red curve, however, is the aliased components due to the imperfections in the stop band, which have been reflected and get superimposed on the audio signal. So you sometimes see, should I evaluate my filter with or without some decimation? Well, that's the difference which occurs. Red curve is just in-band frequency response errors. Blue curve are the aliased components due to subsampling. Remember, it's been subsampled by a factor of 4 from 176 to 44 kilohertz. And so there's those two components. So when you have a sampling rate converter, there's these two areas. Any ultrasonic information potentially gets aliased due to imperfections in the stop band, and ripples in the actual pass band cause errors as well. And there's a second example. This is a much better filter, 401 samples, a much narrower stop band of 100 hertz. The left-hand curve shows it a bit ragged, but that's simply due to truncation of 24 bits. And again, the same sort of example. You can see we see similar errors, but as you would expect, they're of lower magnitude. Notice, however, how the errors rise as we approach 22 kilohertz. So there's a gradual increase in all errors, both alias and in-band ripple, as we approach 22 kilohertz. These may be audible, depends. At least they're errors, whether they're audible or not, we can at least agree that they're errors. So, what is this new big idea? The idea I call spectral-domain matching. Let's imagine, for simplicity, we'll have a 2-to-1 conversion ratio. So we start off with samples in what I'll call the input bit frame, and we're going to create samples in the output bit frame. The idea is we take blocks of data. So we start off with 8 samples in the input bit frame, and we're going to create 8, it doesn't have to be 8, this is just by way of example, 8 new samples at half the sampling rate in the output bit frame. And what we need to do is to compute, for a random choice at least for a set of input samples, we need to compute the output samples such that the spectra of the input and output are matched as closely as possible in the 0 to 22 kilohertz region. What happens beyond this? We're using this as a, well, maybe not 22 in this case, but we're going to use it as a subsampling filter, as a downsample rate converter. So the idea is we must match the spectrum of the input and output over the band which will become our active band in the output waveform. Now to do this, we can do it by matrix techniques. You can construct a matrix, so we apply, for example, 8 input samples, and we compute 8 or 16, whatever it is, output samples. We have to calculate what the coefficients of the matrix have to be, but we only have to do that calculation once. Once we have our matrix for a given input bit length and output bit length, we can then apply it to these waveforms. This is actually an example, and you can see the coefficients in the slide for the B coefficients and the amplitude of the input coefficient. And you'll notice there's no time, very little time dispersion. There's only the output block frame. There is one caveat, however, and that is that the output samples are complex. They're not real samples, they're complex samples. They have 2 dimensions. So we have to design a complex D-to-A converter. We have to adapt our hearing to listen to complex sampled audio. Other than that, there's absolutely no problem with this. I'll come back to the, you're wondering now, what the hell do you do now? Okay, I'm going to consider 2 examples again. In this case, it's going to be a 32 sample sequence to illustrate the spectral domain matching. So, we take 32 samples, we're going to match it to the output samples. And here's the result of applying the matrix, which I would have created to do the conversion. The black curve is the input samples, the red curve is the output samples. You'll notice up to just over 40 kilohertz, but they're very, very close. The curves sit on top of each other. That's what I mean by spectral matching. Of course, the phase must be matched as well. So, because this is complex business. So, the phase and the amplitude are matched. Now, what it does at the higher frequency, the fact it doesn't match, doesn't actually matter, because that's beyond the order of the spectrum, and we're going to subsample anyway. Now, you may say, do those components get alias? The answer is no, because we accurately spectrally match the signal in the audio band. There is no aliasing. Not directly, providing we do the spectral matching. Proof of the pudding. Here's a 4-tone intermodulation test. Started off with a DXD signal, that's 8 times 44 kilohertz. Made it up of 4 input frequencies, 19 and 20 kilohertz, and 67.3 and 69 kilohertz. Then do 4 times downsample rate conversion with outputs being quantized to 32 bits, so you can see what's going on at low level. And you can see the 2 waveforms. There's different types of filter used in the reconstruction, but you can see essentially on that example there is no difference between the 2. Noise level is down at -200 dB, which is due to the 24-bit coding and obviously the length of the spectral analysis. There's no intermodulation effects, and either from the ultrasonic stuff up at 69 and 67, and there's no intermodulation between 19 and 20. So the technique is essentially linear, giving an exemplary spectral performance. Another one, I like this one, took an input signal, I don't know, nearly finished. He warned me. He's got a hook hidden just outside. He did say when in the invitation I had 5 hours. What went wrong there? Yes. Okay, DXD again, this time a white noise input signal. But one proviso that it has a stop band built into the input noise between 1.5 and 5 kilohertz. It's applied to the technique, the downsampling rate converter is applied, and there's the output spectrum. And what's significant in this diagram is that you can see the flat frequency response, and you can see that in the stop band, it goes right down to the noise floor. There are no intermodulation products of all that high energy noise falling into the stop band. It's dead clean. There's a slight trace of an error. As we approach 22 kilohertz, but it's very, very slight. It's within a few hertz of the half sampling frequency. There's 1 or 2 parameters you can adjust to give you a slight angle on that. But the response is extremely flat, almost up to 22 kilohertz. No intermodulation distortion. Wonderful. It can also be used for DSD. It doesn't have to be LPCM. DSD is PCM, it just happens to be 1 bit. Same thing. In fact, it loves higher sampling rates. This was a 64 times, or what's that, 2.7 megahertz, down converted to 88 kilohertz. It shows 88 kilohertz because I wanted to show you the noise floor of the sigma delta modulator. It's a Sony algorithm, it's a classic design, it has 2 notch filters, and you can see that the technique has preserved the noise in that waveform. Extraordinarily accurate. So it works brilliantly for DSD. In fact, I tend to convert my DSD tracks down to 88 kilohertz and then truncate them at 24 bits or even 32. There's no reason to throw away those bits other than file size. And you can convert it down to CD size too, and that really, with a mono sampling, that seems to work very well as well. Okay, we're moving on. I hope this demonstration is going to work. I've got a demonstration courtesy of Glucose Records, who provided the track we're going to listen to. The track is called Celebration by Fiona Joy. It's on her signature solo album. It was mastered by Glucose Records at 5.6 megahertz DSD. I then converted it using the spectral-domain approach down to 88.2 kilohertz. So I'm just hoping it's going to work, guys, if we could play the track. I think it was 1995, I published a paper with the IEEE. They had a local colloquium on audio. And there was a proposal in that for actually looking at a way of coding the ultrasonic information and embedding it in the digital audio stream. So you could have a signal, basically it's CD standard, with the data buried inside the audio information, making it compatible with CD as well. Well, of course, we've now seen the emergence of some commercial products claiming, or like doing that, not claiming. But what I've done is to adapt the spectral domain approach to actually embed ultrasonic information at 44 kilohertz and use the lower bits in the system. And it does it in a way which has a certain degree of bit allocation in it. So the amount of, if you like, damage it does to the in-band signal progressively gets less as the sound level falls. And so what we can do, if you take a 24-bit file, for example, then it's only going to affect the lower 8 bits of that 24 bits, and it will only affect 8 bits for very high-level signals. Progressively, as the signal goes down, there's a gradual change to a high-resolution system. That recording that you heard had actually been processed down to 44 kilohertz and then reconverted back to 88 kilohertz using the embedded information. Some further work which I've been doing in the spectral domain approach, which allows the information to be embedded in the actual audio signal. And it's perfectly compatible with the CD standard. Well, not, well, you have to truncate it to 16 bits to be compatible with CD, but it's compatible with playing standard 44 kilohertz files. And also, the low-level signal is randomized anyway, so it, from the converter, from the data point of view, it looks like random noise, which tells you a little bit about what I was saying, that the lower 8 bits can really be noise-like without doing very much damage to the signal at all. But probably by the time you're down to about minus 50 dB, then the ultrasonic band drops out and you're back to full resolution. So you get the full 24-bit resolution of the signal. So without any modification or noise shaping or processing, it stays very faithful to the source information, particularly at low level. Right, I said the final finale. See, I got a trick up my sleeve. I'm going to conclude, you know, there was a time where if you mentioned audio cables, people used to burst out laughing and make out it was all snake oil. Well, it might well be. But I want to show you something that might make you feel a little bit different about it. You know, the large scale, we have Maxwell's equations, and of course at the smaller scale, we have quantum mechanics. So maybe the structure of a cable can actually do things to the sound which normal theory doesn't necessarily apply. Now, I've got to thank Armour Home Electronics for performing these tests. They were doing it part of the subjective part as part of product development, but they did some extra measurements for me to try and justify what I thought was going on. They tested 4 cables, okay? And 4 people performed blind tests on those cables. And the process was, they did a round of tests, and then they said which the worst cable was, and they eliminated it. Then they did the test again, and eliminated the next until they ended up with the best one. So the 4 cables were like this. Now what it turned out, each member of the 4 actually agreed. There was no dissension between the 4 people running the test. And they claimed the top-ranked cable sounded best by a significant margin. There were then 2 in the middle, which was hard to tell the difference between. There was a slight bias in favor of one, but there was some uncertainty there. And then there was 1 cable, which was by far the worst. Now, what could be going on? We measure a cable, It has pretty much a flat amplitude response. Normal theory doesn't measure any significant distortion. You know, you do a two-tone intermodulation test, you don't end up with the different signal appearing. So what else could be going on? Well, we've talked about jitter in digital audio and timing errors, and it's pervasive in digital audio in particular. It occurs in digital interconnects. It can occur in analog circuits as well. It's not always recognized as such, but if you have a high feedback amplifier, non-linearity in that circuit can actually modulate dynamically the phase response of the system. The amplitude response stays almost flat. So timing errors of the sort of tens of picoseconds can creep into lots of audio equipment. Even analog equipment isn't devoid of this stuff. So, the tests performed came out like this. I got them to perform some tests with a 1 gigabit per second pseudo-random sequence. They had a very special test set which could do this stuff. And it was possible to work out average jitter figures in the output waveform. Now, the best cable came out with an average jitter of 35 picoseconds, and the worst came out with an average jitter of 253 picoseconds, and the two in the middle were close. They were actually in the reverse order of the preference of the people running the tests. But it was close. There was some dissension there. But the jitter performance is different. And what is even more illuminating is when you look at the eye patterns of the cables as generated. Now, if I were to give you those patterns and say, put them in order, I put the one with the lowest jitter, which is the top left-hand one. Nice wide eye diagram. The eye diagram may not be that significant because these are audio cables, but we're trying to expose jitter within the cable itself. Then we have the second and the third, and actually the one which was on the subjective test, the actual, although it has the slightly higher jitter, it actually looks a better waveform for some reason when you look at it as a sort of pattern recognition thing. And then the worst cable is the bottom right-hand one, which has the highest jitter. So I put it to you that there are micro things going on within cables involving the dielectric, involving the conductors, which actually manifest themselves as a form of jitter in the cable. And because it's jitter, and these things are only picoseconds, remember, so when you measure a frequency response, all that stuff gets averaged out. You don't see it, so it looks perfect. You test it on an intermodulation test, it looks perfect. Now, the fact you're seeing jitter, and we're doing a very high frequency test here, but because it's jittering at high frequency, doesn't mean that the actual audio information isn't being jittered as well. It's just very small and very difficult to detect when you come down to picoseconds, just as it is with an amplifier, for example. So I put to you, this is a controversial point. I've not really seen tests which have, you can measure performance of a cable and it's actually agreed with the subjective ranking of the cable, except for the two middle ones, which were very close. But the extremers, the top one and the bottom one, there was no question about. And on an objective measure, it looks as clear as crystal. Okay, thank you very much. Thank you, everyone.
So a very great deal of thanks to Malcolm for tonight's lecture. We've had a tour over numerous different aspects of high-quality audio performance, from analog circuits that are remarkably simple but effective through to an analysis of some of the issues that affect the quality of conversion and sample rate conversion. Malcolm, you are a highly deserving recipient of the Richard Heyser Memorial Scholarship Award, and Jürgen and I would like to present you with a small certificate which would like to honour the the event, and I don't know whether we have a photographer around, but it would be nice if we did. And I'll just pop that down, and we'll.
Okay, wonderful. Thank you. Fantastic.